This will be Calculus section 1.3. This is kind of getting into more detail in the real uses of limits. We're going to be evaluating limits analytically, not with graphs. We're going to be using algebra to actually do this. So let's look at the vocabulary here. It says limits do not always depend on, this should be on, the f of x value, which is the same as the y value at c, which is what x is approaching. Okay, so keep in mind c is this little number here, and then f of x is this function, but it's also a y value. Okay, it says, however, for continuous functions at c, so in other words, if a function is continuous at this value, we can use direct substitution to evaluate the limit. In other words, if we know that a graph is going to go through the point that we're looking for, then that's what the limit is going to be. We just simply can plug our value in. So if we look at this real quick example here, we have 4x squared plus 3. Well, this function right here, this function is continuous at every single point. There is no jumps. We don't have to worry about any discontinuities here. So that's just our function. It's continuous. So if we plug our value in, our 2 in, then that's going to give us a y value. Well, if it's continuous, of course that's the value that this graph is going to be approaching. So when I plug 2 in here, we get 4 times 2 squared plus 3. Okay, so that's 4 times 4 is 16 plus 3 is 19. So again, if you were to look on a graph, if we were to graph this parabola and we were to go to 2, you would see that from both sides of 2, it would be approaching 19. Okay? So let's look at this example down here. We have the limit as x approaches 0 of the square root of x squared plus 4. Same idea. Even though this is not continuous everywhere, what you need to find out is whether it's continuous at 0. So if you can plug it in and get an answer, you're fine. There is no issue with that whatsoever as long as you're getting an answer. So we're going to plug this in. We get 0 squared plus 4 is equal to the square root of 4, and the square root of 4 is just 2. So therefore, the limit of x, as x approaches 0 of the square root of x squared plus 4 is just going to be 2. And if you looked on a graph again, you would see that as x approaches 0, it would be 2 from both sides. Okay, so here's two questions. Why don't you guys try and do these on your own? Hit pause on the video, and then when you're ready, hit play, and you'll see if you got the right answer. So for this first one, hopefully you got the answer of 2. Again, all you're doing is plugging in your 3. So even though this is discontinuous at x equals 2, it's not discontinuous at x equals 3. So it approaches 2 from both sides. Okay, this one down here, plug in 3, we get the third root of 8. This is also 2. So again, plugging in the value gave a solution. Okay, so let's look at one with dealing with trig functions. It's no different. The same thing is true for trig functions. You know, if there's no discontinuities, then we're just literally going to be plugging in values. So this one is the limit as x approaches pi. So I plug that in. I get pi times the cosine of pi. And the cosine of pi is equal to -1. So we have pi times -1 is equal to -pi. Simple as that. Okay, why don't you do this one on your own real quick and hit play when you're ready. So again, all you're doing is plugging in pi over 3. It is continuous at that point. You should have gotten square root of 3 over 2. Okay, so these ones are the easy ones because we have no discontinuities. So now we're going to get into something that hopefully is not really that difficult for you because we kind of reviewed the concept of this. And that's what happens when direct substitution fails. In other words, what happens when you try and plug a value in and you get undefined? That's going to be an issue. So what's going to happen is we are going to try and rationalize our function. In other words, we're going to try and see if we can cancel something out. So if we can cancel out the portion that causes the direct substitution to fail, then we can still use direct substitution at the end. What does that mean? Well, because x is approaching -3, if we were to try and plug -3 in here, we would get 0. So we would get 0 on the bottom. That doesn't give us an answer. That gives us undefined. What you want to do then is once you find out that the bottom is still going to be 0, so we can't get an answer, you also want to plug it into the top. So if I plug -3 into the top, I get -3 squared plus negative 3 minus 6. This is equal to 0. If I plug negative 3 into the bottom, I get negative 3 plus 3 equals 0. So keep in mind, we can't do 0 over 0. That's undefined. But because the top and the bottom are the same number, it tells us right away, I know that we can cancel something out, that we can rationalize this function. How do we do that? The same way we did it in the review section that we were doing. We will factor the top to be x plus 3 times x minus 2, that's how that factors, over x plus 3. So now you can see this cancels out. And remember, if you recall what we talked about, this would end up being, it's going to be x minus 2 is all we're left with. So we have the limit as x approaches negative 3 of x minus 2. Okay, that's the function that we're going to be left with. So if we were to graph this, this is actually what it would look like. It would be a line that goes through negative 2, and when we got to x equals 2, there would actually be a hole there. This is what we had talked about with the removable discontinuities. If you can remove something, it doesn't mean that the discontinuity goes away. We would still need to put a hole there. So essentially what we're doing is we're graphing the x minus 2, and then the only thing that's going to be different between the a regular x minus 2 line and this line is there will be a hole where the discontinuity was, which was at x equals, sorry, this wasn't in the right place. It should be at x equals negative 3, so it'd be down here. So I apologize for that. But the idea is the discontinuity is still there. It just becomes a hole because we removed it. Now, how do we find the limit? Well, there's no more discontinuity at negative 3, so now we can plug in negative 3 minus 2 is equal to negative 5. So once you have eliminated the discontinuity that causes the error, we can then still do direct substitution into the final product to get what our limit is. And if you can see this line, if this is where our hole was down here, somewhere around there, if this is negative 3, you can see that as we approach from the left and as we approach from the right, it's approaching negative 5, the y value. Okay, so that's essentially what we're doing is we're figuring out what will the y value be as we approach both sides. It does not matter whether there's a gap there or not. It does not have to be defined for the limit to exist. As long as it's converging on the same point, it will always exist. Okay, why don't you try this one on your own, same concept, and go ahead and hit play when you're ready. So in this one, the idea was to factor the top. We eliminated our discontinuity, which was at x equals negative 2, because the x plus 2's cancel out. We're left with x plus 3. Plug in the negative 2 into our function, and we get 1. Again, this would be a straight line as a graph, but there would be a hole at x equals negative 2. But that does not mean that that limit doesn't exist just because it's a hole. It would look almost the exact same thing as this, except the line would look a little bit different. So hopefully this makes sense. This is the first part of what we're doing in this section. Hopefully it's the easier part. Don't forget, if an Edmodo quiz has been assigned on the Edmodo page, then make sure you do that, and I will see you in class.